Thank you very much. So Halcyon allowed us to iterate and move very fast with the development of Pika Pika. A major goal of Halcyon is to minimize or eliminate busy work, something I call artist metadata meshes. So show me one artist that actually enjoys making these meshes over something more creative, and I'll guarantee you they're brainwashed, needing an intervention in our caring support. Another critical goal is the live reloading of all assets. We don't want to take a coffee break while shutting down Halcyon, launching a data build, coming back and resuming whatever we were doing. One luxury we had by starting from scratch was choosing our feature set and min spec. We decided to only target modern APIs so we're not restricted by legacy. Another interesting goal is to provide easy access to multiple GPUs without sacrificing API cleanliness or maintainability. To accomplish this, we decided on explicit heterogeneous MGPU, not linked adapters. We're also avoiding any AFR nonsense for a number of reasons, including problems with temporal techniques. Since we also want to experiment with techniques that may not map to average present-day hardware, we have also decided on supporting scalable computation. We scale to all cores in a workstation, multiple graphics adapters, local Kubernetes clusters, and also Google Cloud Platform. We also designed our scaling approaches to work under a single abstraction, which is easy. It wasn't. So we do traditional local rendering, but in addition to scaling computation, we also chose to support scaling rendering remotely and transmitting the results back to the application, such as buffers, textures, or swap chains. In order to deliver on our promise of fast experimentation, we needed to ensure a minimal amount of boilerplate code. This includes code to load up a shader, set up pipelines in render state, query scene representations, etc. This was critical in developing and supporting a vast number of rendering techniques and approaches that we have in Halcyon. We have a unique rendering pipeline which is inspired by classic techniques in real-time rendering with ray tracing sprinkled on top. We have a deferred renderer with compute-based lighting and a fairly standard post-processing stack. And then there are a few pluggable components. We can render shadows via ray tracing or cascaded shadow maps. Reflections can be traced or screen space marched. Same story for ambient occlusion. Only our global illumination and translucency actually require ray tracing at this time. Here's an example of a scene using our hybrid rendering pipeline. And here's the same scene using a traditional pure rasterization rendering pipeline. As you can see, most of the visual fidelity holds up between the two, especially with respect to the materials. Let's toggle back and forth a little bit. Some guiding principles behind our architecture is that there's no concept of a classic frame, and rendering occurs at variable frequency. In addition to the frequency, there's also no promise that data is locally resident, requiring us to design our systems to handle latency and also massive data sets. I'm a big proponent of separation of concerns, where systems are designed for a single purpose and monolithic systems are avoided at all cost. Another principle is that verbosity is hidden with layers. We provide an explicit low-level API to users, which can be used directly if desired. But then there are some convenience APIs on top to avoid the 5,000 lines of code to render a triangle problem I'm sure none of you have seen. There are a number of rendering layers making up our architecture. The application sits on top, for example, Pika Pika, and provides a very high-level abstraction on top of Halcyon itself. Underneath the application are a number of convenience APIs like RenderGraph, and under those are explicit APIs like render commands going to the various backends and device implementations. The first layer I'll talk about is the render backend. Render backends are implemented as live reloadable DLLs. Each backend represents a particular API and provides enumeration of adapters and capabilities. In addition, the backends will determine the ideal adapters to use depending on the desired purpose. Each render backend also supports a debugging and profiling interface. This provides functionality like RenderDoc integration, CPU and GPU validation layers, etc. Most importantly, render backends support the creation and destruction of render devices, which I'll cover shortly. We have a variety of render backends implemented. For DirectX 3D12, we support the latest variant of Shader Model 6, DirectX ray tracing, full bindless resources, explicit heterogeneous MGPU, and DirectML. Vulkan is a similar story to DirectX 3D12. It supports basically the same features, but it has the added benefit of being cross-platform. Additionally, it's much easier to work with GPU vendors to get access. Test. There we go. To get access to harder features through Vulkan's extension system than it is with Direct 3D 12, making it an ideal render backend for high-end research and development. Metal 2 is still early in development, but very promising. We have another pretty crazy backend called Render Proxy, which I'll discuss later in the presentation. Finally, we have our mock render backend, which is for unit testing, debugging, and validation. This backend does all the same work the other backends do, except translation from high level to low level just runs a validation test suite instead of submitting to an actual API. The next layer to discuss is the render device. Render device is an abstraction over a logical GPU adapter, such as VK device or ID3D12 device. It provides an interface to various GPU queues and provides API-specific command list scheduling and submission functionality. Render device has full ownership and lifetime tracking of its GPU resources and provides create and destroy functionality for all the high-level render resource types. The high-level application refers to these resources using handles, so render device also provides an efficient mapping of these handles to internal device resources. First off, I'll describe what our render handles are. So our rendering resources are associated by handle. The handles are lightweight, just 64 bits, and the associated resources are fetched with a constant time lookup. The handles are type safe, protecting against errors like trying to pass a buffer in place of a texture. The handles can be serialized or transmitted, as long as some contract is in place about what the handle represents. And the handles are generational for safety, which protects against double delete or using a handle after deletion. Handles allow a one-to-many cardinality, where a single handle can have a unique representation on each device. There's an API to query if a particular render device has a handle loaded or not. This makes it safe to add and remove devices while the application is running. The handle is owned by the application, so the representation can be loaded or reloaded for any number of devices. Shared resources are also supported, allowing for copying data between various render devices, such as in multi-GPU. And a crazy feature of this architecture is that we can mix and match different backends in the same process. This made implementing and debugging new backends like Vulkan much easier, as I could have DX12 rendering on the left half of the screen and Vulkan rendering on the right half. Another key rendering component is our high-level command stream. So we developed an API-agnostic high-level command stream that allows the application to efficiently express how a scene should be updated and rendered, but allowing each backend to control how this is done, including render state changes and resource barriers or transitions. Each render command specifies a queue type, which is primarily for spec validation, such as incorrectly putting graphics work on a compute queue, and also to aid in automatic scheduling, like with async compute. As an example, here is a compute dispatch command, which specifies compute as the queue type. The underlying backend and scheduler can interpret this accordingly. The high-level commands are encoded into a render command list. As each command is encoded, a queue mask is updated, which helps indicate the scheduling rules and restrictions for that command list. The commands are stateless, which allows for fully parallel recording. The render command lists are compiled by each render backend, which means the high-level commands are translated to the low-level API. Command lists can be compiled once and submitted multiple times in appropriate cases. The low-level translation is a serial operation by design, as this is basically running at memcopy speed. Doing this part serial means we get perfect redundant state filtering. Another important aspect of a new render backend is the translation from a high-level command stream to low-level API calls. Here's an example of translating a high-level compute dispatch command to Vulkan. And an example of translating a high-level begin timing command to Vulkan timestamps. Here's an example of translating a high-level resolve timings command to Vulkan. Notice that the complexity behind fence tracking or resetting the query pool is completely hidden from the calling code. Each backend implementation can choose how to handle this efficiently. Another significant rendering layer is our render graph. Render graph is inspired by Frostbite's frame graph. Just like frame graph, we automatically handle transient resources. Complex rendering uses a number of temporary buffers and textures that stay alive just for the purpose and duration of an algorithm. These are called transient resources, and the graph automatically manages these lifetimes efficiently. Automatic resource transitions are also performed. We call our implementation render graph because we don't have the concept of a frame, as mentioned earlier. Our transitions and split barriers are fully automatic, and there is a single implementation regardless of backend. This is thanks to our high-level render command stream, which hides API differences from render graph. We also support multi-GPU, which is mostly implicit and automatic, with the exception of a scheduling policy you configure on a per-pass basis. This represents what device a pass runs on and what transfers are performed going in and out of the pass. Render graph supports composition of multiple graphs at varying frequencies. These graphs can run on the same GPU, such as async compute. They can run with multi-GPU with a graph on each GPU, and they can even run out of core, such as in a server cluster or on another machine streamed remotely. There are a number of techniques that can easily run at a different frequency from the main graph, such as object space translucency and reflection, or our circle-based global illumination. Render graph runs in two phases, construction and evaluation. Construction specifies the input and output dependencies, and this is a serial operation by design. If you implement a hierarchical Gaussian blur as a single pass that gets chained X times, you want to read the size of the input in each step and generate the proper sized output. Maybe you could split it up into some threads, but tracking dependencies in order to do a construction in a parallel fashion might be more costly than just running it serially. Evaluation is highly parallelized, and this is where the high-level render commands are recorded and automatic barriers and transitions are inserted. Here's an example render graph pass with construction phase up top and the evaluation phase at the bottom. As mentioned, we support explicit heterogeneous multi-GPU. We use a parallel fork join approach, and we copy resources through system memory using the copy queue. It costs roughly 1 millisecond to transfer 15 megabytes of data, so it's important to minimize how much we transfer. This is done by redundantly replicating immutable data to all GPUs, such as meshes and textures, and also tightly packing or compressing data to minimize the transfer size. Our workloads are divided into partitions, where the number of partitions is based on the number of available GPUs. We designate one of the GPUs as the primary device, and the other devices are designated as secondaries. With complex rendering and computation, there are a variety of scheduling and transfer patterns needed. We built a simple rules engine to drive the logic of our workloads. For our ray tracing workloads, the common pattern is to run the ray generation on the primary GPU. Then we copy slices or subregions of this data to the other secondary GPUs, where each GPU performs tracing on its own subregion or partition. The tracing results are then copied back to the primary GPU, and then filtering is performed exclusively on the primary GPU. This approach avoids many problems with temporal techniques and also means we don't need to transfer as much data, such as the full G-buffer, to the secondary GPUs. The workloads are only divided into partitions based on the x-axis or width. This simplifies textures versus buffers, since we can treat all subregions as 1D instead of 2D. Passes are unaware of the GPU count, which keeps the code clean and avoids any edge cases or bugs with untested mGPU configurations. This code snippet shows all that is needed for a pass to scale the workloads, regardless of how many GPUs are in use. The automatic scaling window works quite well for us, but there are lots of fun coordinate snapping bugs to fix up in the beginning, like 3 GPUs partitioning to 0.3 repeating. And then some interesting bugs when we did crazy configurations like 16 GPUs, because why not? Our simple rules engine allows for a pass to specify the scheduling and also request transfers in or out of the pass. The transfers specify what partitions are copied from source to destination, and the transfers also specify rules for the transfer destination, allowing for basic copies, multicast copies, etc. The transfer partition is specified for both the source and the destination GPU, allowing for a variety of transfer patterns. Here's an example render graph pass which specifies the mGPU scheduling policy, in this case to run on all available devices. This example also schedules the transfer of the resultant data back to the primary device. Isolated to isolated means that each device will only copy the subregion or partition that it was responsible for computing. In the bottom half of the code, you can see the evaluation phase, which is scaling the work dimensions for the compute dispatch based on the mGPU configuration. When developing mGPU support for our render graph passes, some scheduling or transfer bugs were obvious. Here's another example. And then some bugs were very subtle, like this weird cell shading. Incorrect transfers would result in input data being incorrect or uninitialized, or result data not being copied back to the main GPU for filtering. Incorrect scheduling would cause passes to not run, to run when they shouldn't, or have an incorrect partitioning window interfering with the work of another GPU. And this bug actually stayed in our build for 2 weeks because people thought the artist did it. Oops. This is a list of some of our render graph passes in Pika Pika. We ended up adding mGPU support to reflections, shadows, lighting, global illumination, and ambient occlusion. The initial implementation of render graph would explicitly chain input and output dependencies between passes, but this led to messy coupling, and also explicit checks like if a depth prepass is already run, import the depth target, and if not, clear the depth target or disable depth. We improved the implementation to support implicit data flow using explicit scopes. This allows for long-distance extensible parameter passing. A scope is given to each render pass, which supports nested scopes for subgraphs, and the results are stored in the scope. Hygiene is provided via nesting and shadowing. The scopes can be looked up by type, such as depth or gbuf resources. The lookup returns parameters stored in plain old data structs. We've also been experimenting with various implementations of a DSL for render graph. Currently, it's using horrible, hacky macro magic, but we're thinking about writing a code generator using Rust, relying on many amazing features of the language to develop our DSL. The goal here is to make render graph fully data-driven and even serializable. Render graph can collect automatic profiling data, presenting you with GPU and CPU counters per pass. Additionally, this works with mGPU, where each GPU is shown in the list. There's also a live debugging overlay using mGUI. This overlay shows the evaluated render graph passes in order of execution, the input and output dependencies, and the resource version information. In order to make multi-GPU development easier, we built something we call virtual mGPU. Most developers typically have just a single GPU in their workstations. It's quite uncommon for 2 GPU machines, and it is rare for machines to have more than 2 GPUs. Having a huge machine is practical for the show floor and cranking settings up to 11, but this is impractical for regular development. Testing these configurations becomes challenging. Our solution was to build a device indirection table. We enumerate available device adapters, and based on a setting specifying how many copies of a device are desired, we redirect our own virtual device indices to actual adapter indices. We do this by creating multiple instances of a given device. Similar to multiple applications sharing a GPU, the OS, such as WDDM on Windows 10, will execute multiple instances of a device sequentially. This approach increases the overall wall time, so don't use it for end-to-end profiling. However, this is amazing for development and testing, even estimating the possible performance characteristics of the mGPU algorithm in isolation. And there's a fun story around this stuff. For Pika Pika, all developers only had a single GPU, and there was very limited testing with 2 GPUs. The show floor at GDC was a machine with 4 GPUs, a configuration we'd only ever tested using virtual mGPU. We crossed our fingers and hoped we didn't make a horrible mistake by relying on this exclusively for testing. The demo worked flawlessly on the first try with the actual hardware and gave us the wall time improvements we estimated. Virtual mGPU even reproduces most mGPU bugs in the same way, which is incredibly useful. Some developers never tested on physical mGPU ever and developed entire features like our Surfable GI using only virtual mGPU, and the night before GDC, I might add. Another interesting capability of our architecture is our render proxy. Render proxy is another render backend implementation, like DirectX 12 or Vulkan, except this allows us to mix any API with any OS. The way it works is our render API calls, like the high-level command stream, get routed remotely using gRPC, which is a high-performance RPC framework developed by Google. This lets us use an API in an incompatible OS, such as using DirectX 12 on macOS or Linux. This is especially nice for bringing up new platforms, as we can get base memory, I/O, and core functionality running without initially worrying about the graphics system. Render Proxy allows us to scale large workloads with a GPU cluster. Render graph passes that support mGPU can automatically scale to the cluster without any additional code, which is a really powerful design. Another interesting property is that only the rendering is routed, the scene state is local. This means that the rendering is based on the actual local version of code and data, which allows for fast iteration and development. This lets us work from the couch, such as using NVIDIA ray tracing with a Turing GPU on a MacBook. With our Render Proxy architecture, the possibilities are truly endless. I also wanted to briefly cover some of the machine learning that we have in Halcyon. Pika uses deep reinforcement learning, trained with Halcyon rendering 36 semantic views. The training is performed with TensorFlow and our on-premise GPU cluster. The Pika demo did in-process inference with TensorFlow using AVX2 on the CPU. We're adding inferencing support with DirectML to Halcyon. This will provide hardware-accelerated inferencing operators. DirectML allows us to do our own resource management, schedule ML work explicitly, and also interleave ML work with other GPU workloads. We're investigating a fallback to other APIs if DirectML is not available. So we can treat the trained ML models like any other 3D assets. We will expose DirectML with render graph abstractions. We want to reference the same render resources and provide a similar approach to chaining compute passes. Similar to our other high-level commands bracketed within a render pass, we will record some form of meta-render commands for ML bracketed together, and this will allow the various backends to fuse or transform these commands for performance if desired. And I wanted to mention some interesting aspects about our asset pipelines. Just like any other engine or framework, we have a variety of asset types that we load from a source or intermediate representation, process with a pipeline, and produce a more optimal representation for runtime. An exciting spin is that for geometry and animations, we've ditched traditional FBX in favor of GLTF. We've also written all our asset pipelines in the Rust programming language, though I'll refrain from getting my usual soapbox and shouting about how awesome Rust is. The cool thing is that all our assets are content addressable. We don't reference resources by virtual file system path. Instead, we only reference by a hash like SHA-256. We use Merkle trees for efficient dependency evaluation. The general idea with Merkle trees is that the leaf nodes are data blocks, which are hashed, and nodes further up the tree are hashes of their respective children. You can test if a leaf node is part of a given tree by computing a number of hashes proportional to the logarithm of the number of leaf nodes in the tree. This allows for efficient dependency evaluation, avoiding redundant network transmission of data, and secure verification of data contents. Our pipelines are all containerized in Linux Docker, running on Kubernetes. We can scale our pipelines in Google Cloud Platform and also in our on-premise cluster comprised of AMD Threadrippers and NVIDIA Titan Vs. Communication between Halcyon and the pipelines is done with gRPC and protobuf, and our content-addressable data is all backed by Google Cloud Storage. Our pipelines support detailed analytics with Prometheus and Grafana. We publish custom metrics to an HTTP endpoint, and these metrics get scraped into a rich UI. We can't stress enough how important collecting data is for profiling how long pipelines are taking, including bottlenecks to improve, and also for tracking down errors and bugs. This is what our on-premise GPU cluster metrics look like when displayed with Grafana. This is a very rich and responsive web UI, and it's very easy for us to add in all sorts of interesting metrics and dashboards for whatever we want to track. Last thing I'll discuss today is how we handle shaders. We implemented a system which supports multiple microfacet layers arranged into stacks. The stacks could also be probabilistically blended to support pre-filtering of material mixtures. This allowed us to rapidly experiment with the look of Pika, while at the same time enforcing energy conservation and avoiding common game dev hacks like metalness. An in-engine material editor meant that we could quickly jump in and change the look of everything. The material system works with all of our render modes, be that pure rasterization, path tracing, or hybrid. And for performance, we can bake down certain permutations for production. We exclusively use HLSL 6 as our source language, and the majority of our shaders are compute. Performance is critical, so we rely heavily on group shared memory and wave operations. We don't rely on any reflection information outside of validation. We avoid costly lookups by requiring explicit bindings. We also make extensive use of HLSL spaces, where the spaces can be updated at varying frequency. Here's a flow graph of our shader compilation. We always start with HLSL compiled with Microsoft's DXC shader compiler. The DXIL is used by Direct3D 12, and the SPIR-V is used by Vulkan 1.1. We also have support for taking the SPIR-V, running it through SPIR-V cross, and generating MSL for Metal or ISPC to run on the CPU. We have a concept in Halcyon called shader arguments, where each argument represents an HLSL space. We limit the maximum number of arguments to 4 for efficiency, but this can be configured. It is important to note that this limit represents the maximum number of spaces, not the maximum number of resources. Each shader argument contains a shader views handle, which refers to a collection of SRV and UAV handles. Additionally, each shader argument also contains a constant buffer handle and an offset into the buffer. Our constant buffers are all dynamic, and we avoid having temporary descriptors. We have just a few large buffers, and offsets into these buffers change frequently. For Vulkan, we use uniform buffer dynamic descriptor type, and on DX12, we use root descriptors, just passing in a GPU VA. All of our descriptor sets are only written once, and then persisted or cached. Here's an example HSL snippet showing one usage of spaces. Each space contains a collection of SRVs and a constant buffer. The shader argument configuration on the CPU is shown below. An important part of our Vulkan backend was consuming HLSL as a source language and fixing up the SPIR-V to behave the same as our DX12 resource binding model. We decided to use the SPIR-V reflect library from HiWin and Cort Stratton. It does a great job at providing SPIR-V reflection using DX12 terminology. We use it extensively, exclusively actually, to patch up our descriptor binding numbers. SRVs, samplers, and UAVs are simple. These types are uniquely namespaced in DX12, so T0 and S0 wouldn't collide. This is not the case in SPIR-V, so we apply a simple offset to each type to emulate this behavior. Constant or uniform buffers are a bit more interesting. We want to move CBVs to their own descriptor sets in order to make the shader views representing the other resource types persistent and immutable. To do so, we don't adjust the offset, we'll have a single CBV per descriptor set. However, we do shift the descriptor set number by the max number of shader arguments. This means if descriptor set 0 contained a constant buffer, that constant buffer would move to descriptor set 5 if the max shader arguments is 4. If a dispatch or draw is using 2 HLSL spaces, the patch SPIR-V will require the following descriptor set layout. Notice the shifted offsets for the SRVs, samplers, and UAVs, and how the dynamic constant buffers have been hoisted out of their own descriptor sets. Let's cover something on tools really quick. So I'll briefly mention some useful tools we use for our Vulkan implementation. For debugging and profiling, the usual suspects were quite helpful and used extensively. Probably aware of them. The API statistics view in NVIDIA Insight is a great way to look at the count and cost of each API call, to figure out if you're calling something a lot in Vulkan, is it actually expensive or not? Because some of them are misleading, and some of them are quite obvious, but kind of need to profile that to see. Another awesome feature with Insight is the ability to export a capture as a standalone C++ application. Insight will write out binary blobs of your resources in the capture and write out source code issues about the API, basically. So you can build this app and debug problems in an isolated situation. Here you can see sort of a dump and basically some standalone solution of Visual Studio loading up with binary blobs that reproduce that one scene. And here's a bug being reproduced in the standalone C++ export that we were seeing at runtime inside of Halcyon in the early days as well, which is some test assets off the internet. With the goal of having everything be live reloadable and live tweakable, we use DRM GUI and imgizmo extensively for a number of useful overlays. So I can't stress how useful this is, where we can basically just select any object in the scene and mutate any properties of it. And I also recommend not writing your own UI system unless you're shipping a game. Yes. On one last note, I'd like to point out that we're hiring for multiple positions at Seed. If you're interested, please give us a shout. Thank you to the Reboot Develop Blue event organizers and Khronos for inviting me to speak, and also to the awesome team at Seed working on Halcyon. And a final note is that I should mention Khronos has created a public Slack workspace shown on the bottom right with the goal of building a great open community around various Khronos initiatives, including Vulkan, GLTF, and others. There are members available there. You can ask questions and get help and participate in some great discussions. And with that, I'd like to open up for any questions you may have.
Thank you very much for the talk, Graham, and you're free to ask questions, and I'll pass you the mic.
Hello. So I just have one quick question. So given all the features and extensibility and debugging abilities that you just demonstrated, what exactly would a quote-unquote real game engine like Frostbite have over Halcyon? So what's the advantage of not using Halcyon for a real project?
Well, I think there's a few things. So the main one, which I talked about in the beginning, was sort of the performance and consistency across all the APIs. Like, we can bring something into Halcyon, we can do an initial implementation of it. We can get some pretty good profiling information. Like for ray tracing, it's like we can get a geometry-only scene exported from one of our games and test traversal performance through it and things like that. But until it's actually in Frostbite, those metrics are kind of a good estimate. So it's nice to sort of work in Halcyon and do the rapid iteration, but then you still need to get it inside of Frostbite to prove it out with other things running as well, because Halcyon has some sort of game component concepts, but it doesn't have the full audio engine running that Frostbite has, or sort of all the AI and all the game behaviors that are also sort of taxing memory buses and other things like that. So it sort of really helps with the rapid iteration of graphics, which is usually something that engines have to put a lot of rigid APIs around to make it fast. But then we can sort of take that transplant into Frostbite, connect it properly, and then sort of get it over the finish line there. Does that answer your question? Great. Any other questions? All right. If you have any other questions, feel free to email me or talk to me on Twitter. I don't mind that at all. So thank you very much.